When dealing with question 5.1, we are required to sketch the graphs of the functions h and f and indicate all relevant information such as the intercepts, turning points, asymptotes, and such relevant information. So prior to answering all the detail, we first ought to identify the class and type of functions that we're dealing with. Clearly h is an exponential function since the independent variable x appears in the exponent of the expression, and f is parabola since this is the turning point form of a parabola and with the highest power of x, exactly 2. I would also like to mention that we will rely on our prior knowledge and experience of dealing with these functions to determine things such as the shape, concavity, and turning point for these functions at hand. We'll also be employing the intercept technique, which is described compactly by this procedure to determine the intercepts. So let's jump right in and calculate the intercepts for the exponential graph. So to do that, we follow this procedure as indicated above. To calculate the y-intercept, we must substitute 0 in the place of x, which is equivalent to calculating the function value at 0, which gives us 1. We then can write this as a coordinate pair, since the chosen value of x was 0 and the corresponding y value is 1. There we have the y-intercept. To calculate the x-intercept, we'll notice difficulty when substituting 0 in y. Now think of h of x as taking the place of y and try and solve this exponential equation, and you'll realize that there is no way in which I can write the bases to be the same. There's no way in which the bases 0 and 4 can be manipulated so that this equation is solvable in x. We therefore conclude that when y is 0, we get a horizontal asymptote. Let's call it the h asymptote for horizontal asymptote. That is in fact the independent variable axis. And the vertical axis here is our y-axis. So we can also identify the shape of this curve, h of x, by identifying that the independent variable x here is positive. So it is an increasing, growing function, with this intercept being the one we calculated in the y-axis. So that is basically what our graph is going to look like. However, we will combine this with the parabola as well on a singular set of axes. To calculate the relevant information and draw the parabola, we follow a similar approach as with the exponential function. To calculate the y-intercept, we set x equals to 0. This is equivalent to calculating the function value of f at 0, which gives us -6. So as a coordinate, to calculate the x-intercept, however, we substitute 0 in the place of y. Now think of f of x as the symbol y, and we will need to solve this quadratic equation. However, lucky for us, there is a shortcut. So since it's already in turning point form, I transpose -8, then I divide by 2, I take the square root, and then I can solve for x. X is 1 plus 2, or x is 1 minus 2, which I can then also write as coordinates. By relying on our prior knowledge for the shapes on parabolas, we can see that the parabola is concaved upwards, right? So an informal sketch of our parabola will look something like this, concaved up with the x-intercept -1, 0, 3 and 0, and the y-intercept. We are yet to determine the turning point TP of our parabola. Okay, so in this case I'm going to use a symmetry argument. Since we can see this distance between -1 and 3 is pretty straightforward, 4 units. So the turning point is halfway between these two intercepts when x is 1. Corresponding y value in the turning point. All we need to do is to substitute 1 in our function. So -8 as a coordinate, we can write it as 1 and a -8. Okay, so a formal sketch will look something like this. Let's just go ahead and fill out all the details as required, as we have already calculated. So the exponential graph you can see here is the y-intercept and the horizontal asymptote, y equals 0. For our parabola, yeah, our turning point is 1 and -8, and our intercepts here is 3, 0, -1, 0. Our y-intercept is 0 and -6. There we have it. That answers question 5.1.